we have divided this roadmap into 4 stages. In stage 1, we learn about the fundamentals, starting with basics of Linux. Here you're going to learn about different commands, as well as some of the important features which the bash shell provides. Following that, we'll become strong in programming using C and C++. After learning C and C++, you can become proficient in data structures to build more complex applications. This acts as a foundation. In stage 2, you learn about the core concept of embedded systems and embedded system programming. Here you learn about microcontrollers and interfacing, and also learn how to develop different applications in domains including automotive, industrial automation, and healthcare. We'll also introduce RTOS module in stage 2 so that you can learn how to build real-time applications effectively. We're going to specifically use FreeRTOS in this module. In stage 3, you're going to learn how to build more complex and advanced applications using Linux. Here we'll teach you operating system fundamentals and subsystems like process, memory, and networking. We'll also cover concepts like IPC and help you build projects using all these concepts. After stage 3, we'll move to the final stage, which is the advanced stage. And in last stage, we're going to learn about advanced embedded development. Here we cover embedded Linux on ARM and Qt programming. In embedded Linux on ARM, you're going to learn how to build Linux from scratch. You'll work with hardware boards, including Raspberry Pi or BeagleBone, as well as emulator. In the end, if you want to develop embedded UI applications, we'll teach you Qt and QML-based embedded GUI programming. These are the 4 stages you will be going through in your journey of becoming a professional embedded systems developer. Very importantly, we have ensured that you're not just learning the concepts. At every stage, you're going to build different real-time applications so that you can understand things practically and also showcase them in your resume. More about projects as well as what companies expect out of these modules will be covered once we have the roadmap of embedded IoT completed. With this, I would like to begin with the embedded systems roadmap. Let me start with the roadmap for embedded systems first. When you want to learn about embedded systems, you have to learn many fundamental concepts before you get into the details about embedded software development. To begin with, it's important to learn about programming language that is commonly used to develop embedded application. C and C++ are the primary languages which are used to develop embedded systems. There are other languages also which can be used, but C has been the de facto language used in embedded systems, primarily because embedded systems are having resource constraints. When you're going to work on resource constraint environments, C is quite efficient. We're not going to talk about assembly. Yes, assembly is used in some places wherein you want to develop embedded systems from scratch, maybe at the bootloader level. After C, you can learn C++. Now, there has been a trend wherein companies are asking candidates to learn about C++ because hardware resources have become more powerful. C++ can also be used in developing embedded applications likes of smart TVs, industrial-based UI-based applications, automotive dashboards, and so on. After learning C and C++, you can take a path where you want to become strong in designing data structures and algorithms. In data structures and algorithms, we're going to focus on how to design the ADTs like linked list, stacks, queues, etc. You learn about searching and sorting algorithms. Now, why ADTs are important? Why algorithm analysis is important? When you build complex embedded systems, you'll end up designing software which needs to be efficient. To design efficient algorithms, you have to learn about these fundamental ADTs. Plus, you'll have to know how you can analyze your programs in terms of space and time complexity. So we'll teach you all these essentials as part of the data structures and algorithms course. Moving on, the core of the embedded systems is microcontroller programming. When you talk about embedded systems, microcontrollers are the heart of the embedded systems. Designing embedded system software and hardware requires you to have knowledge about microcontroller architecture, peripheral interfacing, and protocols. In our course, we are not going to focus upon embedded systems hardware design. Instead, we're going to focus upon embedded systems software design. To learn microcontroller programming, should have good understanding about microcontroller architecture and how it works. You have to learn about peripheral interfacing, starting with simple peripherals like GPIO, ADCs, then moving on to protocols like UART, SPI, and even automotive protocols like CAN. The approach we're going to take in making you understand embedded system programming is more of a generic approach. We'll teach you all these concepts in a general way, but you can use it to apply it on any of the microcontroller architectures, including PIC, ARM, and the likes. So microcontroller programming can be done in different methods. One is you can start with bare metal approach, wherein you can learn to program everything from scratch. This approach requires you to understand the peripheral interfacing by reading the data shield at a detail level. You'll end up creating your own header files by defining the registers. You will end up writing your own low-level drivers, post which you're going to build the applications. There is another approach wherein you can take a library-based approach. For example, if you're going to work on STM32-based controllers, STM32 provides an IDE which is called as STM32 Cube IDE, wherein you can take an approach of using the HAL libraries available to build applications without really getting into the details of the low-level interfacing. In our case, we're going to take a hybrid approach. To start off with, we're not going to put much pressure on you. We'll let you use the HAL approach, wherein you're going to learn about peripheral interfacing by using the libraries. Post which, we'll switch to bare metal approach, wherein you'll create your own header files, your own low-level drivers, then build applications on top of it. So this is a unique pedagogy we have created so that students and professionals who do not have any background can easily get into microcontroller programming. Now, talking about the controllers, you can use any of the controllers, including PIC, 8-bit, 16-bit controllers, or you can use ARM M3, M4 series of controllers, which is based upon STM32. Moving on, after learning microcontroller programming using a HAL and bare metal approach, wherein you're going to write programs using state machines and super loop approach using interrupts, etc., we have understood that companies request you to build more complex applications which are time critical. So we introduced another module called as Embedded RTOS. In Embedded RTOS, we're going to learn about the fundamentals of RTOS, real-time operating systems. And in this module, we're going to teach the essentials of FreeRTOS, including core concepts like multitasking, inter-task communication. In the RTOS module, we're going to use FreeRTOS as one of the embedded RTOS. There are several other RTOSs available like Zephyr, VxWorks, etc. But for our course, we have chosen something which is open source and easy to learn. In the FreeRTOS module, we're going to teach you about the core essentials, including scheduling, multitasking, concepts related to context switching, and more advanced concepts like synchronization, inter-task communication, etc. We'll also tell you the difference between developing traditional applications using a non-RTOS approach. Also, we'll also emphasize on using RTOS to develop complex applications which cater to several industrial use cases. After learning RTOS, you can stop your journey here. So many of the companies look for skills like C, C++, microcontroller development, and RTOS. With this, you can start your career in embedded systems. But we never know what the companies expect for. We've seen that several companies expect you to know more complex application development by using full-fledged embedded operating systems like Linux. This is required when you're going to build more complex applications, which you may not be able to build using RTOSs like FreeRTOS. Linux is quite versatile and it's quite commonly used in embedded applications. So our next module is Linux internals. In Linux internals, we're going to cover about operating system architecture. We'll discuss about user space and kernel space. What are the different subsystems inside the Linux kernel, including process management, memory management, networking, and device I/O. We'll also talk about scheduling concepts. We'll also discuss about process management. We'll learn about several system calls, including fork, wait, exec, which is used to create and manage processes. Apart from this, we're going to discuss about multi-threading. In FreeRTOS, you learned about multitasking. Multi-threading is a similar concept. In multi-threading, you learn about how to improve the efficiency of a program by writing several smaller units, which is going to handle different functional units. So multi-threading is an important concept to learn as an embedded engineer. Apart from that, we'll cover important topics like thread synchronization. When you talk about multi-threading, often you run into situations wherein you end up corrupting the data. To avoid corrupting the data, use synchronization primitives like mutexes and semaphores. These topics will be covered extensively in detail because this is one of the favorite topics which is asked by interviewers. So we'll explain these concepts in a practical way using real-world assignments and applications which you can very well explain during the interview process as well. After multi-threading, we will cover about networking concepts. We'll start with TCP/IP protocol, explain how the TCP/IP layers are going to function, how they interact with each other. Then we'll also cover socket programming. So knowing the theoretical concepts will help you understand the fundamentals of TCP/IP, but it's important for you to learn how to build client-server applications using TCP/IP and UDP protocol. So this is what is going to get covered in Linux internals and networking module. So we are at stage 3 now. What next? Right. So you can take two paths. One is a path wherein you're going to learn about C, C++, data structures, microcontrollers, RTOS. Another path, you can specialize in Linux internals. After this, you can further upskill. So we have introduced two other modules. One is Embedded Linux on ARM, and other is Qt and QML. In the last stage, you're going to learn how to build embedded Linux from scratch. Often you'll be given hardware which is based upon some custom board, or it may be developed from scratch by your organization. Given that situation, it's important to understand how you can bring up the board from scratch. So since Linux is open source, we will teach you the concepts of building Linux from scratch. Before that, we'll talk about concepts like board bring up, wherein you have to understand the different layers involved in developing complete Linux from scratch, including topics like U-boot, building the kernel, building the root file system, and eventually building your application and building a custom Linux package. So Embedded Linux on ARM module is more about customizing and building your own Linux operating system for a given board. In our case, we're going to use boards like Raspberry Pi or BeagleBone to build the custom Linux operating system. In case you don't have a board with you, not a problem. We wanted to facilitate you to learn these concepts using an emulator called as QEMU. So QEMU is a popular open source emulator which is available, wherein you can do cross-compilation and run your own embedded platforms without the need for purchasing any hardware. Post this, we will teach you embedded GUI development using Qt and QML. Qt or Qt is a framework which is quite popular in developing embedded UI-based applications. I'm sure you're fascinated by seeing the user interface in a car. If you look at a car, modern cars have two user interfaces. One is an instrument cluster which is going to display information about the health of the car and also information coming from the sensors like speed, current gear, and the likes. You also have an infotainment system wherein you can use it for navigation. You can use it to play your audio video tracks. You can also use it for other functionality like viewing your camera, etc. Now, Qt and QML can be used to develop these type of applications. In our course, we are going to help you learn Qt and QML by building applications like media player, which is going to sit in a car infotainment system. We'll also help you to build more advanced applications like instrument cluster in a car. Isn't it quite fascinating?
And with this, we have come to an end with this video. Roadmap from beginner to embedded systems and IoT professional. If you have enjoyed listening to this video, please like it and you can comment on any of your doubts and queries. We will reply to them at the earliest. And do look up for more videos and playlists and subscribe to Emertxe's YouTube channel to learn more. Thank you for watching.
Different real-time applications so that you can understand things practically and also showcase them in your resume. More about projects as well as what companies expect out of these modules will be covered once we have the roadmap of embedded IoT completed. With this, I would like to begin with the embedded systems roadmap.